Good morning, everyone. Thank you again for joining our weekly seminar. You can see on the screen our speakers for the next few weeks. Please join us for next week's for the other speakers' presentations. Today, we're privileged to have Dr. Eric Wang as our speaker after about a year again. And he's going to talk about his research since the last time he presented in our seminar. As a reminder, Dr. Wang is an assistant professor of computer science and engineering at UC Santa Cruz. And his research area is at the intersection of computer vision and machine learning and natural language processing, with a focus on building embodied AI agents. His research has been recognized by several awards, including the CVPR Best Student Paper Award in 2019, Google Research Faculty Award in 2022, as well as 3 Amazon Alexa Prize Awards during 2022 and 2023. And with that being said, I leave this session to Dr. Wang.
Thank you. Thanks, Mohammed, for the nice introduction. And I'm very glad to be here today to talk about my research on building generalizable, efficient, and trustworthy multimodal embodied agents. Okay, so everybody is talking about ChatGPT now, and it is a very powerful tool for as a large-scale language model to communicate with human users, right? It can do lots of things, and certainly there are some limitations of ChatGPT, like sometimes it would go the fact wrong, and sometimes it would do hallucinate a little bit. But let us ask 2 different questions. First, this is the question I asked to ChatGPT. Can you describe this image in natural language? So I provide the link to my profile photo, and it said, I'm sorry, but as an AI language model, I do not have the ability to access or view external images, right? And therefore I cannot provide a description, blah, blah, blah. Okay, that's okay. Then we can ask another question. Okay, can you grab a drink for me, please? And as you can imagine, the ChatGPT model certainly cannot do that because it's not physically capable of getting a drink for us, right? So you may wonder, why do you ask those 2 questions? It is a pure language model. Certainly it cannot look at the images and do something physically for you, right? Exactly. The problem is that it is a pure language model, right? So if you think of artificial general intelligence, would you think of ChatGPT as our final destination? Certainly not, right? The pure language models has lots of limitations and cannot do over 99% of the tasks in the world for us. So my research is mainly focused on building embodied agents that can see the visual environment, the visual world through their eyes, chat with human users in natural language, and more importantly, act in the real world, like to interact with the environment, to perform some real world tasks. So for example, we may deploy a robot, a home assistant robot, to do some household chores for us, or we may ask them to do some patient care in the hospital, or we may navigate autonomous drone to do some military tasks, right? So there are lots of things they can do. And here is I would like to dive into the technical part. I would like to show you a demo our Java's agent in the AlexPride symbol challenge, which is basically to build such a embodied agent that can converse with human users in natural language and perform some task in this simulation environment. Okay, and in this example, the task is to use the freeze ray to make an ice cold soda. Okay, so the robot, the agent, has no prior knowledge about the environment, so it needs to understand the natural language instruction and the visual environment and do some sort of reasoning to complete the task. Okay, here is a recording of my student. Okay, let me.
Alexa, pick up soda can.
Here we go. Ready for action. By the way, just a heads up, the sub-goals on the top left corner contain instructions on how to complete the task. Feel free to read them, and I'll do my best to follow your lead.
Place the soda can on blue shelf and turn on the freeze ray.
I'm working on it. Off we go. You have completed the task.
Okay, so as you can see, to complete the task, the agent needs to understand both the visual environment and the natural language instruction from the human user. By the way, the agent itself does not have the access to those mission goals shown on the screen. Only the human user can see those mission goals. And this is actually available on the EcoShow devices. If you have an EcoShow at your home, you can play with our boat in this simulation environment. Just see something like play with robot, then the EcoShow device will show you this fancy environment, and then there are 10 university teams participating in this challenge. So you would play with one of the 10 boats developed by those 10 teams. So by chance, it could be our robot. And if you have some unexpected errors, if you experience some unexpected error, it's probably not ours. I'm kidding. So, but our bot has been top ranked for a long time on the leaderboard. Okay.
Alexa?
And so yeah, that's kind of the end goal, right? So and to bring that into the reality, and there are some fundamental problems to solve. And today I would like to talk about 3 fundamental problems in multimodal embodied AI. First, the multimodal representation learning is really the foundation of this, like how to learn a powerful representation model from the data of multiple modalities, like to make it to understand both visual information and language information, as well as some other information, right? And then we will talk about the development of embodied AI tasks, and more specifically, I'm going to talk about our recent work on compositional vision and language manipulation. And in the end, we will briefly mention some ethical considerations of those intelligent agents as they are interacting with human users every day in some very sensitive environment. Okay, so first I'm going to talk about multimodal representation learning mainly from 2 perspectives. The discriminative modeling perspective and generative modeling perspective. Okay, so as you see, most recently, we have witnessed a new surge of deep learning models, right? And this time it started in the NLP area, such as BERT and GPT-3, and then vision transformers in computer vision. And now it also revolutionized vision and language. For example, OpenAI's CLIP model, DeepMind's Flamingo model, and the very popular diffusion models for text-to-image generation. And those vision and language models are actually very powerful for few-shot learners. You can easily adapt those pre-trained models on a bunch of vision and language tasks, as well as some pure vision or pure language tasks. And for example, the CLIP model turns the traditional image classification task into an open vocabulary prompt image matching problem. So here is an example of the traditional image classification pipeline, right? Given an image, the image of a cat, we typically train a model on certain labels, right? Like cat, dog, and bird. This model would predict a probability distribution of a fixed label space, right? And then, so in this case, the probability of the label cat is the highest one. So we predict that this image is a cat image. However, what if we have an image whose label is out of the fixed label space, right? In this case, we only train the image on labels such as cat, dog, bird, but then we have the image of the UC logo, then the model has no idea what it is, right? So, but CLIPs change this. CLIP, by pre-training the CLIP model on a large scale external resources for image and text alignment, then we can easily, what we only need to do is to have a list of text prompts, including UC logo, and we use the CLIP model to calculate the cosine similarity between the image and each text prompt. And whoever gets the highest cosine similarity, then we assign it as the label of this image. And in this case, UC logo can be such an open vocabulary text prompt, and then the CLIP model would be able to predict it, even though it may not, we don't need, even though we didn't really explicitly specify any class labels in the training phase. And okay, so as you can see, zero-shot results, those pre-trained vision and language models can do zero-shot learning, but zero-shot results are not always good and usually suboptimal. And meanwhile, the model size of those foundation models is huge. Now, the biggest one has billions of parameters, and the model size is becoming increasingly larger. So collecting data for all downstream task or domains is sort of impractical. So the key research question we would like to ask is that how can we efficiently transfer or generalize those large pre-trained models to downstream tasks? And so first, I'm going to introduce our recent EMLP paper, CPL, Counterfactual Prompt Learning for Vision and Language Models. So this is a joint work between UC Santa Barbara and Google. A joint work with the UC Santa Barbara and Google, sponsored by the Google Faculty Research Award. Okay, so you may already heard of prompt engineering. So prompt engineering is a very efficient way to adapt those foundation models to downstream tasks, right? And so you can easily, form a text prompt and then use this text prompt to calculate its similarity with the input image and determine, which is the best match for the image, right? And so on the task of image classification, you can see for those two examples, if we feed the text image with different kinds of text prompt, like a photo of a class or a flower photo of a class or a photo of a class, a type of flower, the accuracy would be very different, even though they are associated with the same image, right? And similarly, for this texture image, you can do some prompt engineering. In other words, you can manually design some text prompts to get a better performance. And this is also applied to natural language reasoning. Like, for example, given this question, and a jungler can jungle 16 balls. Half of the balls are golf balls, and half of the golf balls are blue. How many blue golf balls are there? If we directly ask the model to answer this question, and it just made a wrong prediction. However, if you modify the prompt a little bit and say something like, let's think step by step, and surprisingly, the model could reason those questions step by step and finally provide the accurate prediction. So simply adding let's think step by step can boost the accuracy from about 18% to 80% accuracy. So as you can see, the model performance is very sensitive to different prompts. And if we carefully design the prompt, then we can probably get a better performance. So some suitable prompts can magically improve vision and language models' performance without fine-tune model parameters. However, manual prompt engineering can be very tedious and time-consuming, which often requires domain knowledge. Because you need to basically try a lot of things to make it work, and there is no certain direction to try, and sometimes it requires some domain knowledge. So you need to know how the model is trained, right? And so can we automate prompt tuning for better transfer learning performance? Can we automate this process instead of manually designing those text prompts for better performance? Can we automate this process? Can we learn to compose some text prompts for better performance? Okay, so yes, the answer is yes, we can, and I would like to introduce related work of this, COCO-op, standing for conditional prompt learning for vision and language models. So in this work, basically, they fix all the parameters of the CLIP model and only fine-tune a prompt representation. Okay, and the final text prompt would be this learnable context plus the original class label. And here, these context tokens are learnable and produced by a very small neural network. And so during training, basically only a few examples are provided to fine-tune the parameters of this small network to produce the learnable context, while all the other parameters are fixed. Okay. And it works. And so compared to the zero-shot CLIP, if we provide several examples of the same classes, then as you can see here, the COCO-op paper method can boost the performance by more than 10%. Right? However, this method still suffers from poor generalization to answering classes. So if that's for some classes that are answering during this few-shot learning, it even degrades the performance, right? It performs even worse than zero-shot CLIP. So the generalizability is still not pretty good. So prompt learning can liberate us from manual prompt engineering. However, it can often produce spurious, inefficient, or entangled representations in practice, which cause the poor generalization to unseen classes or concepts. So that said, maximizing the predictive accuracy does not really prevent spurious features, right? So how do we solve that? We believe counterfactual reasoning can really help here. Counterfactual reasoning is basically the ability to learn from limited prior experiences by imagining the outcome of an alternative action that could have been taken. So our human brain has a powerful counterfactual reasoning ability. And we can easily, think of those alternative scenarios and imagine what could have been happened. And so in this case, for more efficient transfer learning of vision and language models, we can do counterfactual intervention by asking what if questions in prompt learning. Okay. For example, here, given, say, 2 images and their corresponding text prompts. So the left image is associated with the prompt A, a large long train on a steel track. The right image is associated with prompt B, a large long train on a steel track near a bar. Okay, and you can see those 2 images are pretty similar, and their text prompts are also similar. But the key difference is between those two images is the bar near the long train track, right? Right. So we can actually ask what if questions to identify the key difference between those 2 images. Like, say, what if we add a bar to image A or remove the bar feature from image B? Will the prompt be changed? Yes, right. If we add a bar to image A, then image A would be better associated with prompt B instead of prompt A. And similarly, if we remove the bar feature from image B would be better matched with prompt A. So the key idea here is to construct counterfactuals by identifying minimal non-spurious feature change that causally causes concept change. And then we can learn more generalizable prompt presentations from both factual and counterfactual examples. The ground truth image text pairs are the factual examples we have, and then we can also construct counterfactual examples to boost the generalizability of those prompt representations, right? Okay, so to achieve that, we first introduce controllable counterfactual generation process. First, a non-spurious feature shall be a sufficient cause of the label, right? In the previous example, the minimal non-spurious feature should be the bar feature. With or without it could lead to 2 different text prompts. So we would like to generate counterfactuals by identifying minimal non-spurious feature that causes the label change. Then a counterfactual is a combination of positive sample and negative sample. So, okay, so then we can construct the counterfactual example as a linear combination of a positive sample and a negative sample. Here, V represents a positive image feature, and the V bar represents a negative image feature. And U is the coefficients of the feature vector, right? And see, basically, the V prime is the constructed counterfactual. Okay, so we would like to capture the non-sparseness by replacing the essential non-sparse features only. In other words, we would like to minimize the amount of feature change to the original feature to the positive image feature V that can causally incur label change. In other words, so we would like to minimize the coefficient U here such that the label of the counterfactual example becomes the negative label. Okay, so see, basically, the counterfactual example is a combination of the positive image feature and the negative image feature. And we would like to keep the maximum of the positive image feature and the minimum of the negative image feature. But the final label of the counterfactual would be negative. Okay, then in that case, in that case, we basically identify the minimal non-sparse feature change that can incur the label change. So the learning objective is to minimize u here, the coefficient u here, such that the label of the counterfactual, constructed counterfactual, is negative. Questions? And okay, and again, in the previous example, so we would basically like to identify the minimal feature change, which is the bar feature, and add it to the positive image feature, such that the constructed image would be labeled as a negative, right? So we add the bar feature into image A such that the label of the revised image A becomes prompt B. Okay, so all right. Okay, so and in order to do that, we need some negative examples, right? And of course, we can do random negative sampling, and it works. However, we argue that good negative samples should have different labels, but are difficult to be distinguished while their semantic representations are close. So we utilize the most semantically similar negative examples to generate those counterfactual examples. And so to do that, we first measure the text similarity between the prompts with broad score, and then choose the negative samples with the highest broad scores. And we did an ablation study between text-based negative sampling and random sampling. So both sampling strategy works and can boost the performance. However, the text-based negative sampling strategy is more efficient and effective. As you can see, the broad score sampling strategy achieve better performance on image classification, image text retrieval, and visual question answering. And here we also visualize, the amount of feature change between the positive examples and the negative examples. So first, by looking at the visualization here, you can see, the broad score sample examples are indeed much more semantically similar to the positive image here, and also the amount of feature change actually makes sense here, although it is not always human interpretable. And then finally, we do joint optimization of counterfactual construction and prompt learning. So we propose a joint optimization framework. So it's not like, we first do counterfactual construction and then we fix the examples and then learn the problem. We do those two steps all at once simultaneously. And so for counterfactual construction, we basically generate the counterfactual image features with the minimal feature change that can maximize the negative prediction probability. And then in addition to that, we also do counterfactual problem learning. And we utilize contrastive learning to learn the prompt that can guide the CLIP model to explicitly distinguish between factual images and the counterfactual images we have constructed. Here is the learning objective. Okay, so there is basically here we minimize 3 losses: the cross entropy loss, the original learning objective for the CLIP model, for fine-tuning the CLIP model, and the contrastive learning loss here, as well as the counterfactual construction loss. Okay, so we demonstrate the effectiveness of our CPL method, counterfactual prompt learning method, on 10 data sets across 3 tasks: image classification, image text retrieval, and visual question answering. As you can see, here are the results on image classification. First, you can notice that the COCO-OP method does not generalize well on ANSI classes. You can clearly see its average ANSI performance is even worse than zero-shot CLIP, right? And in contrast, our CPL method achieves clear advantages over COCO-OP for both SIN and ANSI classes across almost all data sets here. And the average performance are clearly better. This is the result on the task of image text retrieval. For image text retrieval, basically each unique text query can be viewed as a label. So the whole test set is ANSI because there are no exactly same text queries between the training data set and testing data set. And we test on 3 different settings, 3 different few-shot learning settings. The one with only 0.5% of the training data, and the one with 1% of the training data, and the one with 3% of the training data. As you can see, CPL outperforms COCO-OP consistently across those 3 different few-shot settings, which indicates that CPL learns better prompt representations and more effectively explores the limited amount of training data we have. And CPL also achieves better performance on the task of visual question answering. As you can see, the performance boost is very significant here, and similar to the task of image text retrieval, the whole VQA test set is ANSI. And we also notice that incorporating the category information into the task relevant prompts can further improve the performance. Like, say, if we, inform the model that, this question is about asking numbers, or this question is asking about is a binary question, the model can perform better. Okay, so to conclude, problem learning is an efficient transfer learning strategy for operational models, but it usually suffers from spurious correlations that cause poor generalization. Counterfactual prompt learning learns more non-spurious and generalizable prompt representations. And we also demonstrate its effectiveness across 10 datasets on 3 major tasks. And CPL performs the best consistently on both SIN and ANSI concepts. And we also believe, the CPL method can be applied to the pure natural language reasoning task and vision tasks. Okay, so that's our recent attempt more generalizable and efficient representation learning for discriminative tasks, right? And so next, I'm going to talk about our recent work on generative tasks. Training free structured diffusion guidance for compositional text-to-image synthesis. This is the joint work with using Santa Barbara and Google. Okay, so text-to-image generation basically aims at synthesize high-fidelity images given a text description. And state-of-the-art text-to-image generation model are able to generate very photorealistic images with stunning results, right? And it's really impressive. And I'm sure lots of you have tried, the stable diffusion model or the DALL-E model to generate some images. And the results are stunning, and it can do lots of things, right? It can be used for virtual interior design, game design, artistic creation, photo editing, or visual advertising. But behind the scene, so yes, text-to-image models generate high quality images with complicated scenes and objects like here. It can generate a very creative image of a professional photograph, an astronaut riding a horse on the moon, right? However, they fail to bind colors to the correct object, even with very simple prompts. So it has a serious attribute binding issue. Let's look at a few examples. So here, given a text prompt, a red car and a white shape. As you can see, the generated result has an attribute leakage issue, right? So it actually generates a red shape instead of a white shape. So it misrecognizes, the attributes here. Another example, a brown bench sits in front of an old white building. Again, the attributes of those objects are interchanged in this case, right? And another example, a blue backpack and a brown elephant. Okay, in this case, you see the elephant is totally missing in this generation. So we would like to ask, can we find a principled data efficient method to improve the compositionality of those generated images? Or more interestingly, can we not train a new model from scratch and simply do some magic on the pre-trained model without even fine-tuning to improve its compositionality? So we phrase, the whole model. There is no learning involved at all. So can we propose a training-free method, which is extremely data efficient, right, to improve the compositionality? So we may need to inject some binding knowledge into the model somehow to do that, like to generate a faithful image, a red car and a white shape, and another faithful image, a blue backpack and a brown elephant. Okay, so the answer is obvious yes. Yeah, that's why I'm here today to introduce this work. But for a quick background, Stable Diffusion is a pre-trained diffusion-based model that iteratively synthesizes an image from a noise pattern. It adopts clip text encoder for text encoding and a cross-attention mechanism to align the text prompt and the generated image. Okay, so we have observed some interesting stuff. First, the correct binding knowledge is free in linguistic structures. Like if we do a semantic parsing of the text prompt, we can easily bind the attribute and the object together, right? But can we incorporate such linguistic structures into the diffusion guidance process through the cross-attention layers? So can we somehow inject those linguistic knowledge to enhance the compositionality of those models? So to achieve that, first, we encode each noun phrases separately and substitute the embedding sequence of the full prompt. Okay, so specifically, we first do parsing of the original text prompt, and we obtain the parse tree, right? And then we can easily separate those noun phrases with both the attributes and the objects. And in order to not, confuse the attributes of those objects, then why don't we just encode each noun phrase separately, right? Then there is no, when we use the clip encoding to produce the contextualized word embeddings, then we can do that separately. Then there is no concept bleeding between different objects. So we encode those each noun phrase separately, and then substitute, the embedded sequence of the full prompt here. So here, for example, here you can see we can encode the noun phrase blue wall first, and substitute the corresponding word embeddings with this separate encoding without any context of the other noun phrases. So therefore, the semantics is strengthened here, right? And similarly, we can do that for the other noun phrases. And so eventually we would have, a list of word embedding sequences. And then we can compute multiple values from the modified embedding sequence. So we use, the modified embedding sequence to attend to different regions of the feature map here. See here, basically, in this case, we will also have, the original word embedding sequence to add a global context. But in addition, we have each word embedding sequence for per noun phrase, right? And we can calculate the cross attention between the word embedding sequence of each noun phrase and the visual feature map. So, we know we need to emphasize blue wall here and the white sheep there, right? And eventually we multiply the values with attention maps and weight the output. The output would be a weighted sum of all those values. By the way, as you can see, there is no training at all in this case, right? No training at all. So it is totally training free, and we can directly modify the pre-trained weights in this way and inject those linguistic structure. And here are some results. Okay, so we compare our method with the stable diffusion model and another diffusion model called composable diffusion model. The stable diffusion model is a bad one. Anyway, we can basically apply our training free method on top of the stable diffusion model. And as you can see here, we can look at the first example for a red sphere and a blue cube. As you can see, the stable diffusion model confused about the object, right? It generates two spheres, even though the color attributes are correct. While our structure diffusion model can faithfully generate the those two objects. And we can exchange the attributes of those two objects. See, a blue sphere and a red cube. Again, our model works better. And then we can look at the second example here, a red bird and a green apple. You see, there is a serious, concept bleeding issue, right? Or attribute binding issue in the generated results of the stable diffusion model. The bird is not completely red. The bird is rather, red and green in this case. And in contrast, our stable diffusion, our structured diffusion model can generate it better. And here is another example for green apple and a blue ball, right? And in addition to qualitative evaluation, we also conduct quantitative human evaluation on the generated results and to compare, different methods here. As human users, humans should be the final judge of all those, right? So we evaluate our method on two challenge benchmarks, actually the binding prompt and concept conjunction prompts. So then, as you can see here, we do a point-wise comparison between stable diffusion and structured diffusion, between stable diffusion, between composable diffusion and structured diffusion. In both cases, our structured diffusion model receive, the most votes from human users, right? Okay, so to conclude, despite the advance in text-to-image generation, some simple problems like attribute binding remains challenging to existing models, including stable diffusion, W2, imaging, and etc. Structured representation from the language domain, such as linguistic knowledge, can serve as guidance for binding the correct attributes to objects in the visual domain. And our structured diffusion method provides a new angle to tackle those compositional problems with training-free and neurosymbolic diffusion guidance. Okay, so that's the, next I'm going to talk about some certain embodied tasks for human instructed embodied agents, right? So then I have to mention the task of vision and language navigation, which is to navigate a robot inside visual environment by following natural language instructions. And here, we can ask the robot to grab the plan for us and then maybe provide some fine-grained instruction for the robot to navigate inside the house and finally reach the destination, right? And so in our most recent survey paper for vision and language navigation, we identify 3 key components of those kind of tasks: the agent, the environment, and the oracle. The oracle could be, another agent or a human user. So then the agent is supposed to communicate with the oracle in natural language and act in the environment to perform the tasks. Okay, there are already tons of methods for vision and language navigation. And I would like to mention our CVPR 2019 paper, which received the best student paper. It introduced, the first reinforcement learning method for vision and language navigation to leverage extrinsic and intrinsic rewards. It also introduced, the first method to allow the agent to pre-explore the environment and adapt itself to new environments. And from the task perspective, we can categorize, all those vision and language tasks from 2 perspectives. First, for the task objective, so whether it is navigation only or it requires some object interaction. So first, For fine-grained navigation, basically, we provide some fine-grained instructions, a very detailed instruction that can guide the agent step by step. And then we can make it more advanced, like only provide some coarse-grained instructions to go to the kitchen and grab me a drink. So the agent does not have step-by-step instructions, like where to go, turn left or turn right. So it needs to reason about, the path and do something. Or, we can make the agent to not only navigate to somewhere, but also pick up something and actually do something. From the communication perspective, so the agent could be, passively receiving all those instructions and just work on it without any further interaction with the human users. Or, the human users could provide some additional instructions, or maybe, the agent itself can ask some questions for clarification. So there is a free form dialogue between the agent and the human user. Okay, so, but for all those existing embodied agents tasks, there is a certain problem. So in those tasks, we assume that the object would be magically moved to the hands of the object, the hands of the agent. So in other words, so we simplify the object manipulation process. So if the agent produces an action like pick up the apple would be just magically moved to the hands of the agent. So the agent doesn't really need to know, how to move its hands and to actually pick it up. So we would like to solve this one last mile issue for embodied agents, vision and language manipulation, which is to manipulate the robotic arm with language guidance. And so then I would like to also mention in the conventional robotic manipulation task, they have the real interaction with the environment. However, those tasks often lack the representations for complex task variations. So for conventional robotic manipulation, basically each task is viewed as a fixed category. So there are no compositionality, no compositionality across tasks. So each task is just viewed as a numeric label here. So okay, so next I'm going to introduce our VLM bench method, our VLM bench paper, which introduced a compositional benchmark for vision and language manipulation. This is a joint work with U Michigan. And so since there are no existing benchmarks for vision and language manipulation tasks, we need to consider 4 requirements, including categorization, generalization, compositionality, and scalability. And to do that, first we propose an automatic manipulation solver called AMS solver, and which can automatically generate those compositional tasks and their expert demonstrations. So in principle, we decompose the manipulation task into a combination of specific actions and target objects. For example, here is an example of the pick up and place task. So the actions in this case contains pick up and place, and the target objects contain the star and the blue container. So, and those actions also include some unique action types like pick and place, stack, pull, open, with some motion constraint. For example, here, for the task stack the blue star on the red star upright, the robot need to move its hand in a certain way and rotate the star so that it can be perfectly aligned to the red star. And for the target object, we introduce an object-centric descriptor for each object here, which contains variants of properties, including the class label, whether it is articulated or not, the color information, the size information, and the relative position information, as well as the grasp pose information. Like, so we basically introduce an automatic algorithm to label those grasp pose information, so that we know in what way this object can be picked up or can be manipulated. And here we show an example of the variations in the pick and place unit task. Okay, and this example typically requires the relative positional reasoning, like pick up the left cube and place it into the left container. So based on our AM solver, we build and collect a new benchmark, VML bench, and it contains 8 tasks from constraint categories. Pick and place, stacks, drop pencils, shape sorter, pull, wipe, use drawer, and use drawers. But there are numerous task variations in terms of different colors, different sizes, different relative positions, shapes, directions, levels, amount of object, and action types. And our dataset also provide, some observations, some raw visual observations, such as RGBD information, instance segmentations, and point cloud, and also, the information of the robotic arm. But whether you are using those information for training your model, it's really up to you. And here are some examples. This is an example of the Go constraint tasks in terms of different shapes, different sizes, different objects, and different colors. This is a demonstration of the path constraint tasks. The robotic arm has to move and manipulate the bottle in a certain way to pour the water into the container. In addition, we introduce a baseline model, 6D clipboard, that leverage the pre-trained clip model and cross attention mechanism to make 6 degrees of freedom key point prediction. And this is the first model that can do 6 degrees of freedom key point prediction for this for those vision and language manipulation tasks. I'm not going to dive into the details of this, but you are welcome to read the papers for more details. And so we compare this model with some 2 variants, the language only agent and the vision only agent, to demonstrate, the essential, the essentials of, the vision and the language information in this task. Meanwhile, we can observe that 6D clipboard agent can solve some tasks, but there is still a huge improvement space. And the vision and language information both play important roles in those tasks. And the ability of compositional reasoning will be critical to the success of those tasks. Okay, to conclude, we introduce an AMS solver for automatic VLM task generations. So then we use the AMS solver to collect a new benchmark VLM bench for training and testing on VLM tasks. But note that we released the code base for everything, and people can also use the AM solver to generate even more VLM tasks. And then in addition, we introduce a baseline model, 6D clipboard. Okay, and so meanwhile, I'm happy. I'm currently advising 3 AlexPrize teams for those for the symbol challenge, taskable challenge and sociable challenge. So the goal of Symbol is, to learn an agent that can perform a task for humans by conversing with humans, right? And the goal of the taskable challenge is to do the opposite, like to provide some guidance for the humans to perform some tasks, like to cook some dishes. So it can serve as a helper there to provide a recipe in multimodal format. And for the social bot, it is basically a chit chat bot. So you can easily, communicate with you can easily talk with a social bot, and the goal is to keep the user engaged in this conversation. Okay, so for the last part, since I believe last time I already mentioned this work, but so here I'm going to skip this part. Basically, this work is to preserve the data privacy in both training and the inference stages. We introduced the first federated learning framework for vision and language model to do that. And okay, so all the works introduced in this talk are available online, and their code and models are also released. Feel free to try them. And thank you very much.
Thank you so much for this extensive and informative talk. I guess we're already beyond the limit of this talk, but please feel free to reach out to Dr. Wang if you have any questions about research presented in this talk. They seem very exciting and on the edge, especially given the extreme interest that ChatGPT and autonomous agents have received in the community. We'll see you next week. Thanks for joining. And I guess we'll meet on my link, right?
Okay, thank you.